Hello, in this video we will explain how to compute estimate of a random variable using a collection of IID observations. So the setting of our problem will be the following. We will assume that we have a collection of observations x0 and up to x capital K minus 1, and we will assume that all of them are IID, which means that they are independent, statistically independent among themselves, and identically distributed. Identically distributed. So all of them are independent realizations of a random variable that we will call, all of them come from the same distribution that we will call P of x given S, which is a distribution which depends on some parameter S. Just as an example, we will assume that this distribution is an exponential distribution. Okay? S exponential of minus xs for any non-negative x and a positive parameter s. So the target variable is the parameter of the distribution. Okay. So how can we estimate s in this case? Well, basically we can apply the same theory we have studied for the case of a single random variable, because we can just group or pack all the observations in a single vector whose components are all components of all observations. Okay? So in that case, we can just apply the maximum likelihood principle and estimate the parameters ML as the value, maximizing with respect to S the posterior probability of the observations, in this case set, given S. Okay, and well, in this case, this density function is the probability density function corresponding to all observations given S. And now we can apply the independence property. Because of the independence, we know that the joint density can be decomposed as the product from 0 to capital K minus 1 of the densities corresponding to each one of the random variables, each one of the observations. Okay, and we know that all observations, this is a mistake. This is the product of the density of each one of the observations. Okay? And now we can apply the identical distribution property. We know that all observations are identically distributed. And therefore, all these probability density functions are actually the same are P of x given S. Okay. Well, we can simplify a little bit the maximization problem, just applying the logarithm. Maximizing this function is equivalent to maximize the logarithm. And this is useful because with the logarithm we can transform the product, the maximization of a product, into the maximization of the sum. The maximization of a sum, which is usually mathematically simpler. Okay, and well, this is the general solution to the problem of estimation, maximum likelihood estimation from a collection of observations. Okay, and now we can just apply this general formula to the particular distribution that we have defined, the exponential distribution. So in this particular case, this is equivalent to maximize with respect to S the sum from key equal to 0 up to key minus 1, this is minus 1 here, of the log of S times the exponential of minus x key S. Okay. And this is equal to the value maximizing with respect to S, the sum from key equal to 0 to capital K minus 1 of the log of S minus x key times S. And this is equal to the value maximizing with respect to S, the sum capital K times of the log of S is just key times the log of S, and with respect to the second term we can take the common factor S out from the sum to get this expression. Okay? And so we have to maximize a function that as a function of S is differentiable for any positive value of S, and the maximum will be in the point where this derivative is 0. So just by differentiation with respect to S we can see that key capital K divided by S minus the sum over key of x key when applied to the at the maximum should be 0, and therefore SML must be equal to capital K divided by the sum from key equal to 0 to capital K minus 1 of x key. Okay? So this is the solution to this particular case. If we are given a different distribution instead of the exponential, then we can apply, well, the formulas in yellow are the same, so we can start from here, from the maximization of the sum of the logarithms of the likelihood of each observation, and carry out the maximization for the any other distribution. Okay. Also, we can apply this method to the maximization, to the computation of Bayesian estimates. So, for instance, in the case of the map estimate, that would be pretty similar. S map is equal to the value maximizing with respect to S the posterior distribution of S given X well, if we have a collection of observations, we would have set here, and we can apply the Bayes rule so that this is equivalent to maximize with respect to S, P of set given S times PS of S divided by P of set in the denominator. And we have to maximize with respect to S, so the denominator doesn't depend on S, is relevant for maximization, so we only have to maximize the numerator. Okay? This would be P of set given S times P of S. Okay? And well, actually we can apply the same steps than before, apply the logarithm and use that. Well, first of all, we can just replace set by the sequence of observations times PS of S. Okay. So you can notice that the only difference with respect to the maximum likelihood is that we have an extra factor here, which is the prior distribution of the parameter to estimate, but we can do the same, and we can also apply the logarithm. So we can maximize just the log of the prior distribution plus the sum from Q equal to 0 to capital Q minus 1 of the logs of the likelihood function of the observations. Okay. So this would be the general formula in the case of map estimation. Okay. And if we had other Bayesian estimators, for instance the mean square error estimate, we had to compute the posterior distribution. That in general it could be a bit more complicated, but in the case of the map estimation, the optimization problem is very similar. The only difference is that we have a new term here, which is the log of the prior distribution.